Have you ever wondered why the coldest temperature imaginable, absolute zero, where everything grinds to a complete halt, remains stubbornly unattainable, no matter how advanced our technology gets? It's a frustrating puzzle that challenges the very limits of physics, and it might just make you rethink what we know about the universe. Around the globe, people use Celsius for everyday temperatures, while folks in the US stick with Fahrenheit like it's an old habit they can't shake. But when scientists dive into the nitty-gritty, they turn to the Kelvin scale. Think of Kelvin as Celsius's cooler cousin. Each degree represents the same temperature jump, but the scale shifts the 0 point down by 273.15 degrees. That quirky number isn't random. It's chosen precisely so that 0 Kelvin lines up with absolute zero, the theoretical bottom where molecular motion ceases entirely and there's zero thermal energy left. But here's the kicker. Despite our best efforts, nothing in the cosmos, from the icy voids of space to our most sophisticated lab creations, has ever touched true absolute zero. And according to our current grasp of physics, it probably never will. We've come incredibly close, though, down to a mind-boggling 0.0000004 Kelvin. So what invisible barrier stops us from crossing that final threshold? Let's break down what temperature actually tells us, starting from the basics to make it crystal clear for anyone new to this. At its core, temperature is a measure of how much energy is jiggling the tiny building blocks of matter, atoms and molecules. In solids, they vibrate in place. In liquids, they slide past each other. And in gases, they zip around wildly. The higher the average energy, the faster and more chaotic the movement, pushing the temperature up. Picture a pot of boiling water. Those bubbles are molecules bouncing with enthusiasm. Cool it down and the frenzy slows. As we approach 0 Kelvin, this kinetic dance winds down to almost nothing. It seems intuitive that if we just siphon off a bit more heat, everything should freeze solid, right? Wrong. That's where the third law of thermodynamics steps in, often playing second fiddle to its flashier counterparts, like the second law that keeps entropy in the spotlight. But don't underestimate it. This law is the gatekeeper of the cold, and this is the part most people miss. The third law isn't just a suggestion. It's a fundamental rule that makes absolute zero an eternal chase. The third law comes in various formulations, but one of the simplest, from physicist Walther Nernst, boils it down like this. No process can drag a system to exactly 0 Kelvin in a finite number of steps. In plain English, reaching absolute zero would require extracting heat infinitely many times, something that's practically impossible, like trying to count to infinity before lunch. Nernst figured this out through hands-on experiments. He'd cool materials step by step, but there was always a stubborn sliver of heat lingering, keeping the temperature just above zero. Later, experts in statistical mechanics showed this isn't a fluke. It flows logically from the other thermodynamic laws, explaining why entropy hits a minimum at absolute zero, but we can't quite get there. Fast forward to modern research, and it's even clearer. Not only do we need infinite steps, but it would also demand an infinite amount of time. Imagine the universe aging forever just to cool one speck of matter. That's how out of reach it is. This ties into broader debates in physics, where some theorists speculate if quantum effects or exotic matter could bend these rules. But for now, the third law holds firm. Bold claim. Could there be a loophole we're overlooking, or is this law as unbreakable as they come? So how do we even flirt with such extreme cold? Let's explore the clever tricks scientists use, with a bit more detail to show how they work in real life. In your home fridge, cooling happens through a cycle that shuttles heat away. Compress a gas to warm it up, dump the excess heat into the kitchen air, then let it expand and chill in a sealed space. Repeat this loop and you've got ice cubes at 0 degrees Celsius. Scale that up for science, and liquid helium can hit negative 269 Celsius or a mere 4 Kelvin above absolute zero. Dip something in a bath of this super chilled helium, and it equilibrates, shedding heat until it's equally frosty. For context, that's colder than the depths of Antarctica on its chilliest day. This method bottoms out around the cosmic microwave background radiation, that faint 2.7 Kelvin glow from the Big Bang, which bathes the universe and sets a natural floor for cooling in empty space. To dip lower, we switch to helium-3, a scarcer version with one less neutron, which can nudge us to about 1 Kelvin. But pushing further, that's where ingenuity shines. Techniques like nuclear demagnetization swap pressure for magnetism. Align the nuclear spins in a material using a strong magnetic field, then release them to cool via entropy drop. Think of it as untangling a knotted rope to release energy. For ultra-precise work, laser cooling takes the cake. Since snagging the 1997 Nobel Prize in Physics, this method uses tuned laser beams to bombard atoms from all sides, like a gentle brake pedal on their motion. Each photon absorption slows an atom a tiny bit, and re-emission randomizes it without adding net speed. Result? Clouds of atoms chilled to fractions of a billionth of a Kelvin above zero. Perfect for quantum experiments, but still not quite there. Even fancier setups, like matter wave lenses, have pushed rubidium atoms 10 times colder, ideal for glimpsing Bose-Einstein condensates, those weird quantum states where atoms march in lockstep like a single wave. For example, in microgravity drops, this lets researchers probe matter's quantum weirdness for seconds at a time. Yet, as effective as these are, they all bump up against the third law. Some residual energy always lingers. Rounding to 10 decimal places might trick your calculator into calling it zero, but physics knows better. But here's where it gets controversial. Ever heard of negative temperatures? They sound like they'd shatter absolute zero, plunging us into sub-zero coldness. Spoiler, they don't. The term is a bit of a misnomer that trips up even seasoned folks. In these quirky systems, adding energy actually lowers entropy, that measure of disorder, flipping the usual script where more energy means more chaos. This only happens in setups with a hard energy cap, like certain spin systems in labs. Think inverted populations in lasers. Far from being the coldest, these are actually scorching hot in practice. Touch one to a normal object, and heat floods out from the negative side. It's a fascinating twist that challenges our intuition about hot and cold. But does it hint at deeper flaws in how we define temperature? Some physicists argue it opens doors to wild engines defying traditional thermodynamics, while others say it's just clever math. What do you think? Does negative temperature redefine cold, or is it overhyped? Drop your thoughts in the comments. I'd love to hear if you agree it's revolutionary or just semantics.